2 or 3 sort of principal theorems and axioms that govern how we train models. While we have explained things with respect to just this raw calculation of grad J, that's actually a massive oversimplification of the underlying mathematical process. Because effectively, grad J is unknown. It's an approximation. So that approximation has to be done through a matrix transform process. So I want to make sure everybody's sort of up to speed on what knowledge you have to have in order to be able to kind of make this all happen. Like I said, I'm sorry today is still a little off for me. I have to grab slides off of my home PC for some reason because they did not get put on my they didn't get put on my thumb drive. So. All right, so let's just start. I'm going to start my mouth though. Doesn't need to go in 394. That would be confusing my 394 students. I one time had an instructor upload a Monte that was for a very different class, and it was very confusing. All right. So let's just think first of all about kind of the principal items that we need to work with. So scalars are items that are pretty obvious to us, right? These are all of our standard variable frameworks. We typically indicate these as italics. One of the reasons why I say that using like A and X as italics for a concept of a scalar is just going to be the notation of like a specific value within our framework, either a value of a feature at a specific point or a value of an output. Vectors, what do we end up with? These are arrays of system information. So recognized first and foremost, we have here a 1D system of rational components. Why vectors are so important is because we're going to use a vector methodology to take into consideration the relationship between a set of weights and a set of inputs across the entirety of a data set, right? So the weights are going to apply to every sample within the system. So we're going to utilize this matrix algebra format, this matrix algebra methodology to create a lot of shorthands for things that we're discussing. That previously I've shown you spatially, right, to construct how those weights, where those weights are located, how the information is propagating through the network. Now we're going to drop it out into the matrix format so that we can do the calculations more quickly. As a matrices process, we can represent either a series of value points or a series of specific information, and structurally, we can represent an entire network via this process. The way in which we do so is we treat each interconnection, right, each layer interconnect for a system as an array relative to the input and to the output of that particular weighted connection between the systems. So that the array is populated for that layer and is composed of each feature, right, and each of its interconnects as enumerated by the set given notation. Tensors, all right, we're going to talk about tensors in a minute. I'm going to show you guys the framework for this. I'm going to switch to my other slides here in just a minute. So these slides are the ones that I don't necessarily prefer, but I'm trying to get my my other slides intact here. Sorry, this is really frustrating to me because I had this all worked out. And I don't know what happened. I'm actually going to pull this set of slides and we're going to pause this. I'm sorry, everybody. You can breathe out this. I appreciate you guys' patience. not hard on me. I didn't hear any sighs of exasperation. You guys are. So this is the only thing I was really able to accomplish, which was to try to put together a better set of slides for you guys, and as a result of somehow not getting them transferred adequately, I don't have them.
It's not just you who are facing with the Canvas problem.
It's not just Canvas. This is actually me not copying stuff off on my thumb drive like I thought I was going to do. So,
Okay.
by the way, Canvas has been out quite a bit.
Yeah,
it's
in the morning
it's
it wasn't there.
Yeah.
For some reason.
I went on to, have you ever seen the Down Detector website? I went on the Down Detector and like the very first thing is this giant spike in structure. And like, okay, apparently it's not just me. So that was really tough this morning because I had another meeting with some students and they
We didn't. We
grab
can't.
their submissions.
Today we cannot give the quiz because of that.
Oh no. Well, these are things we have to deal with.
Canvas was down.
All right, let's start with this again. We'll get over to the other section. So the other was me trying to stall for time. So let's think about the primary items we need to succeed with regard to the calculus framework we have. All right, so we'll talk about those other items again just briefly. I'll give you some visual examples of them. What we need to succeed is we have to understand that the derivative characteristics of any scalar operation is for a constant, you have 0, right? And then we have the multiplication rule, power rule, sum rule, difference rule, product rule. Product rule matters because what we have one function and we have the relevant relationship between that function and some other function as a partial of the decomposition. So we see there we have the partial with respect to g of x and the partial with respect to f of x for both f and g in the composition. But this biggest item that we're interested in from this list right here is the chain rule. Because the chain rule allows us to be able to do a substituent representation of one function acting on another function. That is really important because each individual linear component of the neural network is affected by a function. Every neuron itself is a function. It takes something in and processes it and does something else to it. So you could think of a whole neural network, a long sequence of these elements being passed off as a compositional chain making up the entire perspective of the system in which one neuron is a function acting on another neuron is a function acting on another neuron. So this system right here shows f acting on g of x, right? We could replace x with y, right? We need to say f of g of y of x, right? And you can go even further in, keep nesting that system in further and further. So by understanding that relationship, that the first layer neurons are acted on by the second layer, or acted on by the third layer, or acted on at the output, we can use that process to determine and decompose that sequence relationship back to the individual change in value for some particular substituent weight for a set of inputs. So we can calculate that as an instantaneous value for a specific set of examples to be able to update the network. The idea then becomes that it has a quasi-Bayesian relationship. So we'll talk about briefly, I'll pop back over to the slides that deal with probability, but I want to go through, at least talk with you about some of these topics, okay? Tensors are the last one down there on the bottom. That's the reason why I switched over these slides, because I like these slides better. I think they're funny, okay? You guys have all seen these. This is my favorite one, okay? So the scalar, that's the cute one, right?
Aww.
Just a little dot point. Then the vector, that's That's your wiener dog, right? And then matrix, that's the square one. And then the tensor is a little bulldog, right? It's a little square little guy, okay? What is the tensor then? It's effectively a stacked series of matrices. This is the cube to a single sheet of paper, right? This is the ream of paper. This is a book to the single sheet. Now, adherences from this perspective is that we can represent individual elements within the system spatially coordinately. So we could think about the input could be a two-dimensional system changing through time, or we could also deal with a two-dimensional layer approximation throughout the network as being a stacked series of matrices, because each of the matrices are what? Also can be seen as a type of function, because a matrix is a mechanism of a transform, right? A matrix can operate as a transformation on a vector characteristic. So we're saying here's the input vector, and then here's the matrix that is transforming that input vector, and then as that system is passed through, the tensor is the construct that is made up of each of those individual transforms affecting that original input. Types of tensors, why this matters to us, all right? I'm going to talk about this in the more global sense, beyond just the scope of the immediate goal of backprop, and that is 1D tensors don't really seem to make much sense to us. But at the same time, a one-dimensional tensor system is effectively a single point as an unchanging element, or as invariant substrate of the setup. We tend to think about that as kind of a toning or background tone system, right? It's the generalized offset for an entirety of a data framework, right? A 2D tensor, that's our standard. We know what 2D tensors look like, right? So we have a vector, and then we have a matrix. That's the 2D tensor. When we get up into the 3D tensor, this is interesting because notice that 3D tensor isn't made up of discretized characteristics. I'm not necessarily describing it as a discretized elements. This could be something like a one video, all right? The reason why it's not discretized up into smaller subset samples is because that video is still one object. Though it is made up of individual frames and has a stack of those frames throughout one another, it's still one object. So when we treat it as a third-dimensional tensor, that is one sample. So in our framework of training, usually one sample we think of as like one set of measurements. But from a tensor standpoint, if I have a three-dimensional tensor, I have a 2D tensor that's an individual frame of a video. A 3D tensor is frames of the video stacked together to create some composition of change over unit time. Now the 4D tensor, here's the really interesting one, because we could have a series of three-dimensional information that changes over unit time. What is this type of information? 3D changed with time might be something like a type of media that we haven't had a lot of exposure to yet. VR, right? Yeah. So it's a 3D space, it's a 3D tensor. It shows the entirety of the construct occurring within three-dimensional space, but now we have time samples of that 3D space as it's changing over unit time. The 4D tensor might be used for something like movement tracking or spatial orientation, or, as I said previously, for VR video or VR spatial localization. One of the cool things about this is that if we utilize the right techniques, previously we've had to send the entire 3D tensor at every single frame of the video, right? So now we may be able to come up with a methodology by which to say, let's go back for a second. Think about the idea of compression, right? Compression is a really, really powerful tool for us. Neural networks are actually really good at compression. Matter of fact, they're good at a bunch of different techniques that have to do with things like signal processing and noise extraction. So we understand potentially some of the reasons why. It makes a little bit of sense to us why they're good at it, because say, hey, they can tell which portions of the information are most important at any given time. They can sort of highlight the important regions. Let's think about a 2D tensor as a frame of a video, and then we're going to think about a series of 2D tensors as part of that 3D tensor, right? That chunk of data going into the system. If we don't want to send that whole chunk of data uncompressed, how do we go about it? So we have a series of keyframes, right? Any of you guys had any experience with compression? Okay, so you keyframe, and then what happens? From the keyframe, you determine what has changed between the keyframe and the next frame, right? Usually only one segment of the foreground will actually change from frame to frame. Usually cameras aren't moving around a bunch. They may be some, but usually we don't want a lot of movement. So most images are fairly static. The background is fairly static and doesn't move a whole lot. Doesn't change a lot in color, doesn't change a lot in composition, but the foreground elements change. This is the reason why compression methodologies are good at dealing with things that have relatively static backgrounds, right, with relatively small, slow-moving elements in the foreground. Because all you have to do is describe the 2D tensor to 2D tensor transform from frame to frame, and now the only thing you need to transmit between the frames is what's changed and the matrix of that transformation. Everybody get the reason why I'm talking about this? Everybody tracking with what we're doing here? The methodology by the transformation is very similar to the way in which that matrix is, or that tensor is transformed by the network, right? How much needs to be changed or adjusted within that framework in order to be able to understand it. So the 4D tensor could look and see what's different from 3D tensor to 3D tensor, and we would only have to change what was necessary between frames of the 3D information. What is a 5D tensor? This is the one where it gets really weird. This is abstract. Honestly, some data that I've come across is 5D tensor, some 6D tensor. It just has to do with there having like multiple frames of reference for sort of distilled information in the spatial domain. This would be watching a variety of individual self-contained spaces as they change over time with one another, right? This is each individual room, right? And each individual room is changing over time. The 5D tensor would be a way for us to create a uniform model of how several different 4D tensors were changing with respect to one another. Now we have what? 6D tensor, which is going to continue that process, right? It's a stack of 5D tensors. So what would that mean? We have a series of systems changing with respect to one another. Now we have two different systems changing, or comparing multiple systems and multiple changes of those systems to one another. So the higher we get the dimensionality of the tensor system, the more abstract the conceptual idea of what we might actually be looking to work with is. But still, at some level, right, at this particular level, we could think about a slice of the 6D would be perhaps an incident example, or a slice, whichever slice you want to go into, either the horizontal or vertical slice, right, is a question of what type of data we're looking at, or what an individual time step of that data is. So the individual time step would be a discrete time framework that we would be able to compare and contrast the elements with one another. The selection of the axis, the selection of the angle of the processing, getting the data from something like a 6D tensor into something we can work with in a neural network model. Right now we actually don't have the tools to work with really either the 2D tensor, right, or anything past it. Because what do we have right now? We have the ability to take in vectors of features. So the only information that we're able to actually work with right now with the complexity of the models we've discussed so far are these 1D tensors, just these little vectors. Because we've already taken, right, the two-dimensional information and vectorized it, or we've taken spatial information and quantified it.
I have a question.
Yeah, please.
So now my question is with the 5D, if just a small verification.
Okay.
Like we're seeing one video, and in the 4D we're seeing one video in different timetable, right?
Well,
in 4D.
So actually the interesting part, okay, let me try this one for you. Each one of these is a video.
Yes.
Okay, so let's imagine that somebody edited the video.
Yes.
So this is one version of the video, and then this is the edits they made to it.
Yes.
We're watching how they're editing the video over time, right? So each one is a slightly similar, or maybe correlated version of itself with some changes to it. The other example would be that this is a room, a three-dimensional space, right? And we've quantified components inside of it.
Yeah.
And then those components move, right? So we have to keep the spatial information registered. So you guys understand the concept of registration, right?
Yes.
Getting things to line up. So the spatial registration characteristic would be making sure that each of the 3D tensors in that 4D tensor stack were aligned to one another such that it was a one-to-one comparison.
Okay.
So that if you were in that chair and you moved to that chair in the next frame, everything would be the same between this frame and this one, except for you would be over there in that chair.
Just a small change.
We can look at small changes,
Or we can
look at
do
big changes.
okay? But the conform
What's
is
the
the
challenge
same.
with that? What's the challenge of a big change?
Creates
What if everybody moved randomly by one seat, right, in one direction? That would be a massive change to the framework, right?
Yes.
We'd have to keep track of everybody again. It would only make sense that we would be sampling the system at a high enough frequency to be able to understand when the changes of interest were happening. If everybody was changing all at once, then we might want to try to up the frame rate of our video so that we were taking a better perspective, or take more snapshots of the space so that we were able to adequately understand it. However, there are tools also that would be able to interpolate the frames between those. Right, one of the tools that's really interesting to me is the 3D tensor transform models are actually a form of 4D tensor processing. Anybody ever seen where they add frames to a video? So one of those methodologies, so they take a video that's shot at like 24 frames a second or 30 frames a second, and they up it to 60 or 120 frames a second.
Yes.
Yep.
How they're doing that is by creating the dummy frames, they're expanding it, right?
Yeah, yeah.
And then they're interpolating the frames by comparing the one in front and the one behind. If that was a 4D tensor, right, then we could think about that as the frame, and then the other frame, right, and then this is the one we're going to come back and interpolate based upon the information between the two frames.
Okay.
So you can reorient this to a lot of different tasks as the way in which they're oriented and modeled. Right? So the expansion would be then treated as a 4D tensor, right, or 2D tensor with 3D tensor transform. So that really would be more like a 3D tensor where the 2D elements were spanned to increase the length of the tensor, and then frames were interpolated from the two-dimensional framework. We'll talk about convolution later on. All right, it's a more advanced topic that we don't go into in quite as much detail because the sub-detail of it, while the mathematics we're going to look at, the sub-detail of it is only really important to the acceleration of some of the GPU framework stuff, all right? Anybody interested in that, or is that kind of a tangential thing? All right, a little bit. We might talk about it a little bit about how that framework has been put together, but it's that's a situation where we have to talk about the Fourier transform, all right? We have to talk about how we deal with convolutions in the Fourier space. But convolutions are going to start to come in at the 3D tensor frame, right? Where we're going to have to take into consideration either two-dimensional volumes or three-dimensional volumes acting on the space. So if you take a convolution of a 2D system and you apply several kernels over it, you're actually going to end up with a 3D tensor as a result of that output, right? Or an ND tensor, which is that number of 2D outputs based upon that number of kernels. Right? The reason why I'm mentioning this now is just because I say, let's get used to thinking about what kind of data spaces we're in. This is the kind of weirdness that we can get into. Okay? It's fun, but at the same time, it's relatively challenging. Occasionally, one of the biggest challenges I come across, and I'm going to try and throw a couple of monkey wrenches in the works for you guys, all right? Not big ones, but ones that'll give you a little bit of a simulation of what it's like to work with real-world data. I'm not going to throw you something that's like totally ill-suited for the task, okay? Sometimes people will just give you like, here's an unprepared data set. Go find the outliers and sort it yourself. And it's like, no, that's a little much. All right, so we'll start off with data sets that are better prepared and don't have to deal with as much. But later on, we might deal with some data sets that have some outliers or some confusers or some other stuff in there, okay? So, and we are going to start with the construction of a neural network model. Where I found a video of a guy explaining how to do the programming in Python. It's basically a step-by-step process. But I want you guys to sort of try that and try to implement it alongside of when we're talking about the mathematics. I know we lost a little bit of time, but I will figure out how to make it up, okay? Part of that is going to be that whenever I do the mathematics for you, I'm going to be going over it pretty high level, but then I'm also going to create videos that are going to cut out for those. I have the video, I just need to put the audio over top of it, okay? So when we're looking at something like a list or a data table frame, we can treat the individual components of the vectors of the data table as labels for perhaps orientation of, like, say, a column vector might be a single sample, right? So that column vector would orient to the sample's input, right? And then the last element of that column vector would be the label for that particular sample. The alternative position is to think about the table as a list of vector frames, right? And then something like each of the elements of the column vector would be one feature. And then the last element, the last column of the vector would be the label, right? The target of the system. So depending on how we orient the structure, it's always going to be a system where we have the series or list of features that we're interested in, right? And then the label we're assigning to the end position. I am not going to be talking about much with regard to neural networks that is going to be dealing with unsupervised data. While technically neural networks can deal with unsupervised information, all you are actually going to do is you're going to take the existing understanding of the features and then create a cluster grouping based upon those to have as the target for the neural network backprop, okay? You have to have something to aim for. In this case, it would be some type of loss. That is the difference between what you would hope to have and what you're actually getting. You can't train a neural network whenever you don't have that loss metric in place. Finding new ways to do that is actually a really big part of the innovation within the space, but always you're going to have some vector, some column vector in that last position that is going to be your target. Usually it's either a quantitative metric, right, if we're trying to regress something, or in a classification framework, it's going to be a qualitative metric, a numerical label with a dummy variable. Everybody know what I'm talking about when I describe that idea? Okay, any questions on that? Yes?
It can be, you said at the last, can it be in the middle also? Because sometimes we find the desired data is in the middle, like we need to do.
Oh yeah, I mean sometimes you have to sort it. Okay, what I want to say is this is what you'd like it to be in the end.
Yes.
Go ahead and put that vector over on the far side.
Okay.
The reason why is because when you input your data table into Python, right, go through pandas or something like that, and you throw it into something like TensorFlow, it's going to assume that that last column
Yes,
is
right, yeah.
right, it's going to say, like, that's the assumption, all right? So I'm talking about it from the perspective of, if you're orienting your data, let's say your data comes in, and you could have one feature of that data be the target. So one example is one data set we might use in here. Again, I used in my ISL, and that's the automotive data set. Okay? That automotive data set, you can attempt to regress cost. You can attempt to regress horsepower. You can attempt to regress like the class of the vehicle it is, right? So from that framework, from the data framework, whichever one of those items that you're targeting as the thing you want to predict given this set of elements, you can think of the feature vector effectively stopping right here, right? So the row vector is going to be a single example, right? And then the target is going to be that last index position.
Yeah.
What happens whenever we have multiple outputs? Just the last few are going to be targets, okay? So I'm just saying, in general, what we want to do is we want to have the lead up of our features for the inputs, and then some bifurcation, some partition that's been put in there, right? And we're going to partition the data out in a couple of different ways. Inputs to outputs, right? And then what else are we going to do with it? We're going to bifurcate it according to the training examples versus the examples we're going to use for testing purposes. Everybody experienced that with respect to seeing the test versus training data that was in the TensorFlow example, right? But you want to make sure that you have test and training partitions as well. So test and for example here, what I'm saying is I would cut off these bottom samples and I reserve those as my training set, or testing set, right? So training set, keep the training set, and then my testing set cut off here. They have the same format, and they're oriented in the same way, but they're kept separate. Okay. We'll talk about this probably in a little bit more detail, but self-similarity or identity matrices are utilized fairly frequently with respect to transforms, right? And so one of those principal transformations is going to be the decompositions that we do for eigenvector, eigenvalue, eigenvector decompositions. All right, those require us to evaluate the determinant, and then once we evaluate the determinant, we're going to utilize that as saying that the incident identity matrix of that system is going to be that diagonal matrix that is composed of the eigenvectors of that system. So we're actually going to use an eigenmatrix to act upon the weight matrix for the decomposition. Within indexing systems, we're going to use ANI framework, all right? This will be how I write most of my stuff up on. I also write either JI or JK, or I could write LI. The reason why I say that is that we're going to have two subscripts, all right? Because one is going to compose of which is the input feature or input node characteristic and output node. So typically we work with this configuration which says N is the position of incidence and I is the origination, okay? We say that a value within this matrix is that it goes from target to destination. Okay, target's going to be on your right-hand side, and destination is on your left-hand side. Or excuse me, origination. Say destination. Target and origination, right? So origination is closer, and target is further. So we say that for 1, 1, this is going from element 1 of layer 1 to element 1 of layer 2, right? So that'd be the first weight. And the next consideration, element 1, layer 1 to element 2, layer 2. So we keep that indexing in place. So we typically use row column, right? And row column indicates the relationship of, for instance, passing off as we get further in depth of the system. So we pass further in depth. Okay? Transposes. Everybody remember matrix transposing? What's one of the biggest problems with matrix transposing in neural networks? I would say that it is many matrices do not have symmetry that we can characterize. What's one of the problems with a non-symmetric matrix when it comes to the idea of utilizing a transpose to be able to do something like a element-wise process or dot-style product? Well, there isn't necessarily a known inverse operation. So whenever you have an inverse, you use a transform, right, to rotate a system, you don't always have a strict inverse operation. So we utilize something like the Penrose pseudo-inverse to make an approximation. What this basically says is, if you were to think of a matrix, and you think of each of the rows as its own example of a specific approximate function, you have for each feature, right, that is one variable associated with that feature. When we think about a matrix composed of variables and examples, we would then think of the rows, let's just go ahead and say across the rows, right, relative to columns. If I have a matrix that is much longer than it is wide, what's one of the problems that can happen with creating a single answer out of that system? A perfect n by n matrix would have for one feature, you have one example, right? Where if you have an n by m matrix, you could technically have more equations than unknowns. So that's one of the things we'll talk about along the way, is that technically one of the problems with fitting in regression is similar to this same problem in the matrix fitting with neural networks, is that there are often more example equations or flow sequences of equations than there are actually unknown elements within the system. This means there is not one single perfect answer that will solve that system all the way, so we're going to have to come up with a solution that is best case in that particular example. So eigenvalues and eigenvectors. I will show you guys a couple of examples of these worked, but this usage of attempting to describe the determinant from some example value for the scaling consideration, that A times V, right, for the vector consideration, that the eigenvalue of the system lambda times V is just a scaling factor with consideration to alpha. Best way for me to describe this is that the eigenvector is a special type of vector that for a given matrix, when it is taken as the product, which is what? Is a function acting on that matrix, right? Is a transformation. So when that particular vector transforms that matrix, it only scales it. It doesn't skew it or rotate it. So that special vector that only scales the consideration of the original system is said to be a highly descriptive feature of that matrix. So by utilizing these eigenvalue decompositions, we can make approximations about the understanding of the internals of that matrix by that value of that determinant of the eigen, right? To be able to output both the value and the specific index of the vector for that particular matrix decomposition. I'll try to explain it better with regard to like showing some exact examples, but there's a good sort of visualization that shows that you can skew, if you skew a matrix, right? Eigenvectors are those that will maintain the same relative orientation, right? They'll stay along their span while changing in scale, versus other vectors that are composites within that matrix that change their span relative to the scaling process, become non-invariant components. So we're thinking about invariance. The biggest reason why we're discussing this is that scaling components, the interrelationship between elements across the matrix, across the example, should be what? Relatively invariant. The core understanding of the system that we're attempting to extract are those elements that across the data set, or across the data examples, are maintained with respect to the internal variation of the system. So if we utilize the functional descriptions, that the weights should converge for, or should converge ideally to, that subset version of that ideal matrix. Okay. We talked about this as a perceptron, and I want to go through and describe to you guys a key example here. Notice we have the weight identified by its localization and with respect to its input characteristics. So the weight as described for a perceptron network is one specific type of neural network, okay? I think we talked about it, I think I may have used the terminology before, but the perceptron, also known, it can also be known as a type of Adelaide, is the most basic form of a neural network you can come up with. One of the real problems with this is that we have not yet arrived at the system that we call the universal approximator. So the single neuron, the perceptron, is actually not capable of modeling all known functions. It takes another neuron being tacked on after this, so that you have a hidden layer, or a secondary activation, which is the composition of functions. That would be, if this layer is activation G, right, then we're going to have some activation F acting on G. So we have to have that composition of functions in order to be able to arrive at that universal approximation. We have only linearity in this case. We have multiple lines, but as a result of only having linearity, we can't actually recombine the components of the linear relationship. When you take out the layers from that topology of your original, if you went and removed went to no hidden layers for the TensorFlow playground, right? That would be just the features going directly into the integrator at the end. That's no hidden elements. The only systems that you would be able to solve are those that are linearly separable for classification output, meaning that you could only separate the two cluster system or a very, very easy version of the circle one, right? Which we have, where we have potentially some sort of offset circle, okay? That would be bad. It would be a really, really bad solver for it. It might come out where it's something greater than 50%, but it would be really, really bad solver. Given that this system is very easy to process, right? We say, well, this is easy for us to determine the backdrop system here. How much does this weight need to be updated relative to this level of error? I don't need to do anything other than to just take the relative level of composition for grad J, right, the local instantaneous change. This means that I'm going to have to run it through once, okay, and then I'm going to have to determine the level of error. I'm going to have to adjust some stuff based upon some quasi-random ideal, okay, and then I'm going to have to determine whether or not the value got greater or whether the value got less with respect to the error relative to that weight. Once I have 2 points to compare to one another, I can determine how much the error changed as a result of how much I changed that weight. That's relatively simple. We can just keep running that system over and over again until we min global error, right? Or min mean square error in this particular case, perhaps. As I said, this is the localized linear regression function, but what becomes problematic is whenever you attach two of these together in a sequence, okay? Let me give you an example about getting a better shower. Right, I'm going to explain to you that the whole rest of this is going to be about getting a good shower, okay? This isn't a hygiene lesson for anybody, okay? It's not the whole point. The point is, when you get in the shower, what do you want? You want good pressure, right? So this system is composed of a couple of different elements. The water main outside, right, is where the initial pressure comes from. As a result, we have the actual initial pressure, right, which is set individually for your house, right? How big that line is and how occluded it is. We have a main, which is how much that particular main valve is open and how much of the transition of the water pressure at the pressure head is then being transitioned into the supply lines within the house, represented as X. I then have a handle control, which is at the actual shower head, right? And I have some value Y, which indicates the amount of water that's going through that particular shower. If I have it turned almost all the way off and it's just a little spiddly drip, no, we don't want that. That's bad, right? We want good pressure. We want us to be able to get the ideal amount we're looking for here. But what's the other consideration? Well, we don't want to have it so hard that it, blasts us out. We don't want the main pressure coming and hitting us in the face. We want to be able to have an ideal understanding of how much we turn that handle, right, in the shower to determine the actual amount of pressure we're getting at that point. But here's the reality. There's two controls to be able to make that system balance. Each one has a relative degree of sensitivity. So, for the position given for the change in shower handle, right, which we're going to call position H, all right? We'll just substitute this as delta H. For change in position of shower handle, we might have a consideration for an initial assumption that we start off with position 4 and then position 8, we have some delta 4. Okay, so we moved it, we originally had it in position 4, and then we cranked it up to position 8, and we note that through that transition we had a delta 4, right? We changed the weight, or we changed the permissiveness of that particular valve by that ratio. We have a change rate in the actual shower flow. What is the change rate in the shower flow? Delta Y, right? So if we're measuring it at this edge of the system, we're measuring the pressure coming out as a result of whatever the input is here times whatever the permissiveness of this particular value is for the shower handle positioning, and we have the amount that the actual pressure changed on the output. So per unit change of handle, we have a per unit change in the actual pressure of the output. So I can express this as a ratio of the difference between the shower head's actual pressure change relative to how much I change the handle. Assuming that this handle is perfectly linear, meaning that as I turn it, it opens proportionally. Anybody have a shower handle that performs this way? I don't. Okay? They're not. They don't really work that way. So in reality, this is a very high level example in respect to saying this is the ideal shower handle, okay? The one in the vacuum. But we would then say the sensitivity is that per unit turn of the handle, per 4 units turn to the handle, we're going to get a 2 unit yield in the amount of pressure that was being received at the shower head, right? So we would say then that the change in unit of Y relative to the change in unit of H is a sensitivity metric that can be represented as the partial of the total pressure relative to the handle's change. Why is it only a partial? We saw the whole system earlier. We know that there's another weight there that we can adjust. This is actually the output layer, right? Yeah. This is X. This is X. That's that house pressure, the house pressure inside the system. we have main M, right, a weight, and then the actual water pressure at the street over here on the other side. So if you think about this as the output layer of the neuron, right, your output is Y, that's the target of you getting a good shower, and then the first adjustable component is the handle within the shower, right, but the second adjustable component is the value of the main and how much it is being opened. So we're actually going to calculate this relative to saying that with respect to the handle being changed, we know that there is a effectively 2-to-1 consideration for the partial of Y, right, the partial of the actual output of the system relative to the change in H. This means that the change here, right, is not entirely dependent on this adjustment because we have another handle further out and back. So what are we going to deal with now? We have a change in position M for the main, right? And a change in flow rate X for the actual house flow rate. X is over here on the right, main is there in the center, and the actual value of the input pressure on the system is W, some value W. Now, notice what happens here. Change in flow rate, right, relative to the pressure of the water system is partially responsible or partially respondent for the change in the main pressure. Right? Why? Because actually the input value of the house is set by the street's main water pressure. So I can't entirely just say that the pressure in the house is entirely due to the main. Right? So the difference here is that we can't keep cranking this infinitely to keep getting the pressure in the house higher. We have a limit imposed by a partial differentiation of the respect to which M is open. Now, let's look at the ratio between those. M's change in position is what? 2. Mm-hmm. So per 2 unit element, we have a change in house flow rate, which is from 20 to 16, right, which is 4. So now previously we had a 1 to 2 ratio, we are going to have a 2 to 1 ratio, okay? Numerically, obviously this example is a little bit weak, right, but it's still giving us a scope. Let's look at the whole system together. The change coming from the street through the main, adjusting the flow rate coming through into the handle, adjusting the flow rate out to the actual shower head. This is the chain process by which I was talking, that the forward propagation of the value is set. So if we wanted to get the value exactly to the ideal flow rate for getting that perfect shower, I've got to crank on both knobs, right? Because the sensitivity of change per unit in this particular system indicates what? Only half as much adjustment is available here as is available here. So if I wanted to get down to fine-grained adjustment, I'm going to need to understand how much the partial change of the main needs to be set such that I have an ideal positional range, such that I'm able to use as much of the handle as possible, right, to get the ideal return in the output. So if I make the partial with respect to M of X and the partial with respect to X of Y, look at something that happens here. X is on the top, X is on the bottom. Interesting relationship, right? So I can consider that the change in Y with respect to M can be actually evaluated, right? I can make an understanding of how much actual value of the change in Y relative to that position can be implied. And what is it? If I have X of M and I have Y of X,
these cancel.
they cancel each other. That's a really cool part of it, because we said that as long as these are the reflective partials of change relative to that unit, we can use the chain rule of calculus to say that this system inherits the understanding that M's change with respect to Y is proportional to X, which is the internal pressure of the system. But now I have an expression of not just the handle's change with respect to Y, or X's changes with respect to M, right? I now have an understanding of the pressure at the head with respect to the change in unit M. Now what's actually calculated down here is interesting. We have the the 1/4 relationship for the 1 to 4 offset for the first position, right, times 2 for m, or y of n. Now where did the 1/4 come from?
It came from the previous equations, the two.
Well, the sensitivity for delta H, right, delta H of y was 2 to 4, right? We have sensitivity up there indicating it's 2 to 4. But we're actually not taking the consideration of delta H. Delta H isn't present in that calculation. What is it? It's actually the partial of x, the water pressure, with respect to the pressure at the main, relative to the partial of the head pressure with respect to the main. That is actually the relationship, this is actually the relationship of H, right? It's how much H is able to change per unit consideration. So Y, the head pressure relative to M, that's the mains positioning, has the coordination of Y to X, right, as 1 to 4, because what? We're multiplying it for the unit change in that case. We have handle position, right, 4 here, and rate of change 2 here, but rate of change in this consideration is 2, 4 to 2. So what is x? Partial of x, right, here is what? 4, right? And then y, which is the output rate there, which is 2. What's that consideration?
2.
Delta y, right? 2 for flow rate.
2.
For x2, y of x.
X is 4.
This is going to be 1 unit change of y relative to m is going to be the relationship between sensitivity over 1 unit change in y. So it's 1 unit change in y over the relationship between sensitivity, right? So it actually ends up being one unit of y relative to 4 units n in this case, times 2, which is the sensitivity as given by the change in n at that localization. So m, for every time I change m by 1 unit, I'm actually going to increase x by 2. But for every unit x to increase, right, I need 2 units of the handle to change in position, or excuse me, 4 units of the handle to change in position to reach 2 units of y. So the relationship then ends up becoming 1 position handle y per 4 units handle m times the output value of the sensitivity of m as a result of the system, indicating that in order to reach 1 value of y with respect to any given handle position of h, that the factor m is always going to be a ratio of 1 to 2. I have to turn up m by 2 to get a factor of 1 at the actual output y. Now we've done what? We've created a relationship that says how much delta y can be changed by delta n. So if I look at this whole system together, and I make this first consideration, I make the output that I would like to have y, okay? I'm also going to have a relationship of an error. What is the error in this system? This says the total amount of pressure y relative to the handle change, because this is the portion I'm most interested in, right? I want to use the handle in the shower to adjust the pressure to what I would like it to be. I have an ideal y, and then I have a y that's a product of this whole system of operation. I need to know how much I need to set the main such that when I get in the shower, I don't have to hop back out of the shower and go back out to the main to turn it up, right? So I'm trying to figure out this chain process. I want to be able to make this adjustment closer to the output. So I need to know how much I need to change this so that I have a little bit more flexibility here to get this tuned into what I want. This is the real interesting portion of how the back propagation works, is that you're actually only going to make subtle adjustments to m, but those subtle adjustments are going to propagate to x, and then X's value is changing to give you a little bit more flexibility on H, right? So that you can fine tune it. This is a bulk adjustment, heavy duty bulk adjustment. This is the fine tuning adjustment towards the end here. So we notice that we're going to make larger adjustments to H, we're going to make smaller adjustments to N throughout the process, because relative to what, 2 1/4 in this position is going to give us our error ratio. So you don't want to change M by a whole lot because of what? It has twice the relative impact on Y, or excuse me, on X relative to H to Y, because H to Y has a little bit less control. So E can be seen as Y, that is our ideal output, to Y prime, all right? Y prime is also, I call it Y hat. Okay, we've all seen the hat in statistics.
Yeah.
So the ratio between these is Y to Y hat, or Y prime. Y prime is what our current system of weights has been set to, right? I set M and I set H. I got Y prime. I'd like to have Y. So what do I have to do in order to be able to determine what the adjustments to H and M are to be able to make this ideally suited? We notice something. There is both a reflective characteristic with respect to the total error estimate for Y to Y prime. This is not a parabolic curvature like we're used to with most error surfaces, but what we do notice is that there is a diminishing return in the fine-grained control of M with respect to how well H will respond to that fine-grained control of M. You turn M up too far, and what ends up happening? H will not be able to control it. Turn M down too low, and you can't turn H up far enough in order to be able to allow you to get enough pressure. So on one side, I turn it down too low, and I can't get enough. And on the other side, I get the other diminishing return. I get too high of a setting at M in order to be able to adequately control it at H. So this idea actually creates this sort of discontinuity operation where we have a negative incidence at delta E, or partial with respect to E. Now what is the partial with respect to E for our calculations that we were talking about previously? That partial with respect to E is actually very similar to our instantaneous gradient approximation, right? Relative unit change. So if I were to look at this whole system combined together, I see delta Y per unit delta N has this relationship of 1/2 with respect to the sensitivity of 2 to 4, right? What is that again? 1/2, right? Mm-hmm. So 1/2 and then 1/2 here again. So I see a product relationship again. Interestingly enough, when we actually look at the return error curvature, if we were to set M relative to a series of units, we see the error, right? This is delta Y, which is Y minus Y hat, or Y minus Y prime. Delta H, the change in error, right? The partial of error with respect to H. This means how much of the total error, or how much of the total output is caused by how I set the handle, right? So that first calculation over there, the partial of Y with respect to H relative to the partial of the error with respect to Y, is the product calculation I need to determine the actual adjustment of the weight for H, right? Let's go over here onto the other side. The partial of the error with respect to the main. I've created that as a composition of the partial of the pressure in the house with respect to the main times the partial of the pressure of the head with respect to the pressure in the house times the error with respect to the pressure at the head. This is the chain rule that I chain back from Y to X to N to relate to this is the partial of how much it needs to change for error to be able to adjust to the output at main, and this is how much I need to change the output at H in order to reflect the ideal consideration. So if I set the level of N for 2, for 4, for 6, what's one of the interesting parts of this? This is a nonlinearity. It looked linear earlier, didn't it? Mm-hmm. But when I compose two linear operations, I now have a nonlinear relationship, meaning that per unit change with respect to M, the curvature of total error, or the availability of symmetry for H's error, is a different shape than whenever M is set to 4, when M is set to 6. The sensitivity of that knob becomes far less useful in each of those cases. Notice also, what is the absolute error in this case? Absolute error is all the way down on that graph. So if we think about it, with how fine control we want to get, right? We want exactly the right water pressure. You want to get that perfect shower, right? And it's a perfect thing. This could be water temperature too, all right? Here's another example. I really think water temperature is probably more sensitive. Because once you get the pressure set up, you know, whatever, it's pressure. But too hot, too cold, no, okay? So let's imagine that these mains are hooked up to the hot water supply for your shower, and this is the output of the hot water control in your house. When we think about it, we want to try to get that temperature down to the exact right temperature, right? That's the regulation between, you know, 94 degrees and 93.75, right? We want to be in that space. How do you get that fine grain of control? Well, the fine grain of control comes from the product of delta H with respect to E relative to the set point of delta M given that unit sensitivity. Which of these is the correct setting?
4. Because it's
Why is it 4?
because it's it is
Cheyenne,
close to.
hold on. You answered 4. Who wants to answer why it's 4?
Okay.
I think it's, if I'm reading the graph, the minimum is the lowest for both.
Yep. It's good. Usually minimum's on the bottom. I'm kidding. No, you're right. Okay. I'm being silly. The reason why I'm saying that is you go, yeah, it's absolutely intuitive. The absolute minimum error that could be reached for this system is what? Right down here. We know the shape of the error function changes with respect to the set point of M originally. So we know that the actual adjustability of the knob, no matter how I crank it, it's never going to get to where I want it whenever it's set to 2, right? Whenever it's set to 6. I keep cranking it, and notice something. The curve is getting flatter, right? I adjust it, and because of the sensitivity, the unit sensitivity is the product between the M and H sensitivity, I'm getting less sensitivity at the knob. The best sensitivity is where we have the most optimal flow X relative to optimal flow H, such that H is able to regulate the sensitivity of the transference of X to Y. This is a multi-layer perceptron, right? The handles are the weights. The values flowing between them, the lines between them are the values being approximated or being transmitted through the weights of the system. And this is exactly how we calculate the processes for the ideal set point, right? We're going to regress back through it until we set up with a series of approximations for M settings such that we end up with the maximum return for these two partial differential equations to supply the exact output. Now, what's one of the problems with this? We have 2 weights, okay? What does this look like whenever you have 30, okay? It looks a lot worse, okay? So that's the reality, is it gets a lot more complicated as we get into a bigger system. So how do I adjust this and describe the ultimate perfect relationship between delta n? We said previously we could make the adjustment based upon the gradient J, right? Well, gradient J is the localized approximation of the instantaneous tangent, or the Hessian, of the partial decomposition for the error with respect to the output, right? That's what this is. What is this? This is the weights of the system, right?
Yeah.
Yes.
This is M with respect to Y. Get rid of the X's. Do it in your head already. So this is M with respect to Y. So this is just M. This is the weight of M. What is this?
Series.
Okay, I jump out of the shower in my towel, right? I run across. I crank the knob a bunch, right? Get back in the shower. Handle's not working, okay? The learning rate.
Yeah.
How much per time you get out of the shower and run to the handle, and how much you change it per unit time. Guess what? That's the relationship of how much you're learning, how much you get out of the information that's being presented. The learning rate times the weight, how much M changes with respect to Y, times the relative error with respect to Y for that output is going to be the instantaneous update of how much we need to change. Delta of M for the ideal consideration. We're also going to have to calculate at the same time what? Partial of Y with respect to the handle For the error with respect to the handle, what happens here? Crossed out again, right? Now this is the error with respect to the handle times a small weight adjustment for how much we need to change the handle position to arrive at the ideal state. When I can't necessarily change both of them at the same time, at least with my example is given, right? The reality is that each one of these actually decomposes into a singular value. Each one will provide you with the answer to how much M needs to be changed and how much H needs to be changed. Interestingly enough, you can change both of them at the same time. Why don't we do this in anything else? Right? You don't usually, if you're troubleshooting, do you change two things at once?
No.
No, that's terrible, okay? Weirdly enough, we're going to go ahead and change both things at a time.
Huh?
And then we're going to determine by continuation, because these are partials, right?
Yeah.
I can determine how much each of those changes affected each of the relative errors for the system, because it's a decomposition for the total error of the system as a result of change in M per unit change in H. Okay, that's what we got. What we'll do later on is I'm going to use this notation process. All right, it's very similar. Okay, don't get scared. This is the notation we're going to use with respect to the neural network system to approximate that same process. What happens here? Error with respect to activation times the output of the previous layer times the output of the previous layer relative to the activation at the layer -1, right? Cross out, cross out. The error relative to the activation layer for layer -1. I can keep doing this process and I can determine the level of sensitivity of each individual weight, the total amount of the partial with respect to the error for that specific weight, and I can continue this process back through a multi-layered perceptron, right, in order to design and divine the exact perfect limits for values in this case. Okay, I took up too much time. Thank you guys. Took up 3 extra minutes. I got carried away by our first shot. Thank you guys. I appreciate your patience with me today and appreciate you following through.
I really like that example